Hello and welcome back. Today I'll be going over the AP Physics 1 Algebra-Based answers for the free response questions for the 2024 exam. If you have any questions, let me know in the comment section down below. Otherwise, let's get right into it. So, question 1 here. And the summary of this question is you have a block of mass m and it goes down this ramp, goes through a loop, goes through another loop, and here. And this whole ramp is frictionless, and you start at point A, which is 6r above the ground. So, on to the first question. It's asking us to draw shaded regions in this diagram that show the potential and kinetic energy when it's at point B. So point B is here and it's 2r because you have radius here, diameter is 2r. So let's think about how we can do this. We know the equation for potential energy is mgh. We know we're 6r above the ground and we have 6 bars. So if we're going to be at 2r above the ground, that must mean that we must have 2 bars. Because remember, the equation is mgh, we're now at a height of 2. So just, my drawing's not going to be good here, but you know the basic idea of how to draw it. Ignore this top part here, it should only end here. Now, as per the conservation of energy, since there's no friction, that must mean that since we have 6 bars total here, we have 2 here, that must mean that we have 4 as the remaining for the kinetic energy. So there we go, that's question 1a. You must have 2 over here and 4 in your kinetic area. Next question. Starting with conservation of energy, derive an expression for the speed of the block at point B. So we have to start with the conservation of energy, so let's do that. So what are we starting with? Point A, we're just starting with potential energy. So UGI is equal to, and at point B, we have potential energy over here, so that's UGF, and we do know our thing is moving, so that must mean we have kinetic energy, KEF. So let's continue with that. Our starting potential energy is mgh, so what's our height? 6r. So we have 6r gh, no, that's h, so 6r gm equals, and our final height is 2, so 2r gm plus 0.5 mv squared. And we're trying to solve for m over here. Now, we can divide everything by m, since that's in each term, and we can subtract this 2 over here to here. So now we have 4rg is equal to 0.5 v squared multiplied by 2 and take a square root, and we get this as our final answer. V is equal to root to 8 times g times r. Now you can factor out a root 2 over here, so you can make it like 2 root 2 gr, but they'll accept this as your answer. So your velocity of the block at point B is root 8 gr. Next question. Draw the forces, not components, that are exerted on the block when it slides through point C. So we're at point C over here. Now let's think about one force. We obviously know gravity is acting downwards, but what else is there? Point C is at the very top, so it says the highest points, and we know that in circular motion there has to be a force downwards. Furthermore, if it's sliding through the loop, there has to be a normal force. So that means the 2 forces that we can draw are the force of gravity, so I'll just write a g here. You're supposed to write f of g, but I'm doing this for time's sake. So f of g, and there will also be a normal force here. So like n. So we have a force of gravity downwards, and we have a normal force downwards. And these have to be perfectly down straight, not like this way or this way. Next up, a student claims that 4r is the minimum height of point A, so the block can slide through point C without losing contact with the track. I don't know why it covered there, but it's saying briefly explain why this is incorrect. So let's see, the student is saying that if this was 4r, so it's not 6r, it's going to be 4r, so if that was 4r, then it can slide through point C without losing contact. Well, point C we can see, because this is going to be 2r, and then this is r. Point C is 4r above the ground. The student is saying that I can start at 4a and still be able to pass point C. Well, let's see if that's true or not by using conservation of energy. We know that we're going to start with I'm just going to say 4r. We know we're starting at the height of 4r, and we're ending at a height of 4r. Well, we're starting with the same height, ending with the same height. That must mean that we have the same gravitational potential energy at both heights. And as per the conservation of energy, there's not going to be any kinetic energy at this point. This must mean that the block isn't going to be moving as soon as it gets to point C. So if it's not moving when it's at point C, how is it going to stay in contact and slide through the rest of the loop? It can't, because as soon as it gets here, since it's not going to move, it's just going to fall straight down. So that's why the student's claim is incorrect. So I'm just going to write bullet points here. No kinetic energy. Block will simply fall down. Okay, and then that's just showing it's losing contact with the block, which shows why the student's wrong. That's question 1 answered. Let's move on to question 2. This experiment, so this is one of the experimental procedure questions. So it's saying a student hands a spring of an unknown constant K, spring constant, and as shown in figure 1, the other end of the spring has a small loop, so we can attach the cylinders to the loop. And the student only has access to some cylinders, a stopwatch, and a digital scale. So now we're done with that. Let's move on to question number 2. So this is one of the experimental design questions. And let's look at what we have. We have an unknown spring constant. And, why is that there? Unknown spring constant. We have some cylinders and a hoop to attach the cylinders to. But let's look at what we have. We only have the cylinders, a stopwatch, and a digital scale. So what we have to do is we have to design an experimental procedure that we can use to find the spring constant. So normally I would probably do this using displacement of the spring, but we have to look at what we have. We only have a stopwatch and a scale. So what comes into my mind is the equation for the period of a spring. And if we go up here to our equation sheet, I believe it should be here. Yep. The period of a spring is equal to 2 pi times the square root of m over k, which k is our spring constant. So let's just write that out over here. Actually, I'll draw it out. So T is equal to 2 pi square root of m. M is the mass of the cylinder over k. So what should we measure? The first thing we want to measure is actually the mass of the cylinder. Remember, we have a scale, so mass of cylinder. Something's going off with my spelling today. But there we go. We have mass of the cylinder, and we have another one, which is the period of, so it's the period, so or the oscillation, so time taken for an oscillation. And it's not going to fit in this text box, but it's fine. And what is the quantity we're going to use? So the symbol I'm going to use for the quantity is just a capital T. And for the mass, the symbol or quantity I'm going to be using is, if I could actually type on this, the quantity I'm going to be using is just an m, because m represents mass. Just going to write in m here, and there's nothing else we need. Remember, we just need the mass, we just need the spring constant, we just need the period. So there's no other material that we're going to need. And now it's asking for a procedure. So what are we going to do first? So the first step here is weigh the spring using the digital scale. So now we have a weight. Number 2, we have to stretch. So we have to apply the string. So put the cylinder on the spring and stretch the cylinder down. Record the time for 1 oscillation using a stopwatch. Now, in order to reduce experimental error, what you could do is record the time for 10 oscillations and divide by 10, but I believe that this could also work here. So I'm going to write that. So we record the time for an oscillation, we have the mass recorded, and then repeat steps 1 to 3 for the different cylinders. Because remember, you want to get a variety of data points. Now, indicate the quantities that could be plotted to produce a linear graph in which the slope could be used to find the spring constant. Well, let's look at this. We have period is equal to 2 pi times the square root of m over k. Well, if I want to get a linear graph, I'm not so sure I want a square root in there. So that means I'm going to have to square both sides. So that means on my vertical axis, I would want to be graphing t squared. On my horizontal axis, since we're changing the mass, I want to just graph m. So briefly describe how the slope of the graph could be analyzed to determine the spring constant. So if we were to square both sides, then our equation is going to become t squared is equal to 4 pi squared. I'll just write pi squared. It's going to be equal to 4 pi squared times, and now there's no longer a root here, so it's just m divided by k. M divided by k. Now, we know we're changing m, and this is what our y value is going to be, the vertical axis. So that means that 4 pi squared over k is our slope. So that means that 4 pi squared over k, this is what our slope is going to be equal to. So if we found the value of the slope and set it equal to this, we multiply k to the time side of the slope, we divide both sides by the slope, and we find the value of k using that. So that's how you're going to use the slope of the graph to find the spring constant of the spring. Well, let's go on to the next question. So, well, this is actually part of question 2 still. Nice. In a different experiment, a student attaches one end of the spring, a force sensor that's attached to a wall, and another end of the spring is attached to a cart with a mass of 0.25 kilograms, and a motion sensor is placed here. So we know that this is going to be used to detect velocity. The student releases the cart from rest and the system oscillates. And we have two graphs here, velocity of the cart and force exerted on the cart by the spring. Now, using the data from the velocity time graph, find the change in kinetic energy from 0.5 to 2 seconds. So let's see the velocity graph. So at 0.5 seconds, the cart, let me just write this down. So 0.5 seconds, cart has a v of 0.3 meters per second. But at 2 seconds, which is the next part we have to find, there is no velocity. 2 seconds, cart has no velocity. So that means that the change in kinetic energy is just going to be equal to the 0.5 seconds. But remember, the change is going to be a state function. So that means that we're going to have to do final minus initial. Our final is 0, our initial is a positive number, so our final answer is going to be negative. Because remember, it's ending up with 0 kinetic energy. So we just have to use our equation for kinetic energy, and that is 0.5 times mass times velocity squared. So we just have to put that in. Our mass is 0.25 kilograms, so we can just write that here. 0.25 times 0.5 times 0.3 squared, and we get 0.01125. So that means our change is equal to negative 0.01, was it 1125? 1125 joules. There we go, that is the change in kinetic energy. Next, use the data on the force time graph to estimate the change in momentum from 0.5 to 2.5 seconds. This is our force time graph, so 0.5 to 2.5 seconds. So what we know about a spring and its oscillations is, when a spring is compressed like this, there's going to be a force. But here we can see there is no force, and that happens when the spring is at equilibrium. So if we draw like this point here, when the cart is here and the spring is stretched, like not stretched at all, is just at rest, that's when there is no force exerted on the cart. Because remember, Hooke's law, F equals negative kx, there's no displacement. So no force only happens at equilibrium. And that's when the cart is moving at its max velocity. So if we look over here, at 0.5 seconds it has no force, at 2.5 seconds it has no force. Meaning that at both situations it's moving at its maximum speed. Therefore, there's going to be no change in momentum. So let's just write that there. I'm only going to be writing bullet points because I believe that you guys can write good explanations because you're all physics students. So let's just write this down. So force at both times is 0. Cart is at maximum velocity. I'll write speed actually. Cart is at maximum speed. No change in momentum since the speed is the same. And force applied is 0. Now, use the data from the velocity time graph to confirm your estimation. And let's see, it does confirm our estimation. At 0.5 seconds, it's 0.3. At 2.5 seconds, it's also 0.3. So, at both times, the velocity of the cart is the same. Therefore, there is no change in momentum. That's basically the summary of what you want to write down. Anyways, let's move on to question number 3. You have a beam over here and it's of mass m and length l attached to a wall by a hinge. One end of a string has a negligible mass, so don't have to worry about this, well, the mass. And we have another end of the string attached to a wall above the wall at hinge at point 1. Okay. And the beam remains horizontal and the hinge exerts a force of magnitude f of h and the angle is equal to theta. So the following rectangle represents the beam in figure 1. So draw all the forces. Okay, let's draw some forces now. So we know that, so it says don't draw components, just draw the forces. So we know the string is here, so that's a force of tension. We can just get that out of the way right off the bat. So force of tension. Well, that my T is not connected. Well, that's good enough. But then let's look at the other two forces. We know the hinge exerts a force on the beam of F of H, but which way is this force pointed? Is it going to be inwards or outwards? Imagine if this hinge was exerting no force. Then our thing would not be rotating if we were to cut this string, for example. The hinge allows this slab, this beam, to rotate. Therefore, the force has to be applied inwards. So this is going to be F of H. And now, remember, it doesn't say that magnitude matters, so you just have to draw the force. And now we have to count for because it's saying the beam has a mass of m, so that there is a force of gravity acting on this. But where? Well, it's a uniform beam. So if it's a uniform beam, that means that the center of mass is right in the middle at L/2. So that means that we have a force of gravity right in the middle. And remember, the force of gravity in the middle is very important because we can look at our next questions now. So next up, we have the string is attached lower on the wall, but the beam still remains horizontal. And the dashed line represents the string shown in figure 1. That's this one. So now it's asking, will the tension increase in this second situation? So pause this video if you want to think again, but I'm just going to go with the answer and put this. And this, you'll actually find out why this is once you solve this question, but you need to answer this first without using any equations. So let's think about it. If we look at this from a torque perspective, the only reason the beam isn't moving is because there's a net torque of 0, and the string is exerting a torque on it. Therefore, when you lower the string, the vertical component, because remember the angle is decreasing, the vertical component of the string's force is becoming smaller. And therefore, to keep the net torque equal to 0, the tension of the string has to increase. So let's just write some bullet points. When the angle when the angle decreases, the vertical component of the string's tension also decreases. Now let's extend this. Since net torque is 0, the tension of the string must increase in order to compensate for the lowered vertical component of tension. Now we have that out of the way, let's go on to the actual deriving, and this will support your answer here. So derive an expression for the magnitude of tension, and we have to start by using a fundamental physics principle. So we have Newton's second law in rotational form. So what is Newton's second law? F equals ma. But in rotation, what is that? That's going to be net tau, your torque, is equal to your moment of inertia times your angular acceleration. And we know that this has to be equal to 0 because, remember, this is not moving, it's not rotating, and this is also going to be equal to 0. So how are we going to solve this? We know net torque is equal to 0, and what is torque really? Torque is equal to the force applied times the radius it's applied at. So I'm going to use the text box, it's much easier. So we know net torque is equal to 0, and we have to look at the different torques applied. We have one by gravity and one by the string. So let's write the gravities first. So we have mass m, gravity is this, and it's applied at length over 2. Because remember, it's applied at the middle, length over 2, and this is going to be equal to, so let's look at it. This is the force of tension, and we have to find the tension, so I'm just going to write F, I guess. So the force of tension, and what's the vertical component? The vertical component is going to be F sine theta. So F sine, I'm going to write an O, sine of theta, but we have to look at where it's applied. It's applied at length of L. So when we move on here, we can cancel out the L's, and now we just get mg over 2, delete this, and we get our final answer of the force of tension is equal to mass of gravity, not mass of gravity, the mass of the beam times gravity divided by 2 times sine, this is a bit painful, sine of theta. So force of the tension is equal to the mass of the beam times gravity divided by 2 times sine of theta. Now, does this agree with our justification? I believe it does. When we decrease this angle, the value of sine of theta goes down as well. But since it's in the denominator, the value of the fraction goes up, and therefore force of tension increases. So let's write that down. As increase this, as theta decreases, the angle, the value of sine theta also decreases. Sine theta is in the denominator, so the value of the fraction also increases. Not also, the value of the fraction increases. And therefore, the force of tension increases as the angle decreases. And now, the string is cut and the beam starts to rotate with negligible friction, and sketch the angular speed of the beam as a function of time for the time interval. Now, I actually thought this would be a straight line when I first looked at it, but you need to remember, the only thing causing this beam to rotate is the force of gravity. And at this point, so let's say we cut the string, the force of gravity is completely perpendicular. However, when your beam is like, let's say here, the force of gravity is no longer perpendicular. It's going to be a component that's causing the torque. So that means that the angular acceleration, because torque is equal to IA, this stays constant, but this is decreasing constantly. So this is also decreasing. That means that your graph should look something like, so I'm going to draw this point here. Your graph should look something like this, because the instantaneous angular acceleration is the slope here. So the slope starts off high and then gradually decreases until it's 0 here because it becomes vertical. And when it's vertical, the force of gravity is parallel to the axis of rotation. So there we go. This is what your graph should look like. Something like this. It should be curving like this. There we go. Question 3 is answered. Next, a simple pendulum consists of a small sphere that hangs from a string with negligible mass. Top end is fixed. Sphere is pulled from point A, so it makes an angle. And the sphere is released from rest and swings through the lowest point at point B. So the work done is W sub E. Next, it's being taken to a different planet, and the mass of the planet is the same as Earth, okay, but the radius of planet X is greater than Earth. And we bring the sphere to point A, and it's displaced the same theta, okay, so same angle displacement, and it's released from rest, and it swings to the lowest point, which is point B. And the work done is Wx, and we have to justify why Wx is less than We. So what is work? Well, I believe all of you have heard of it. Well, that's also rotation form, but its simplest form, work is equal to force times displacement. So let's think about it here. We know our displacement's the same because theta is the same, so our force is changing. So why is the force in Wx, so why is the force on planet X less than that of Earth? They have the same mass, but they have different radii. If we go to our equation sheet over here, this is the force of gravity for planetation. This is Newton's universal gravitational constant. M1, M2 divided by r squared. R squared is in the denominator, so if planet X has a greater value for the radius, it's going to have a lower force of gravity. So if we go back over to our question here, let's write this here. Is it going to write? Yeah. Planet X, let's expand this, has a lower radius, has a smaller radius than that of planet Earth. Therefore, it has a lower acceleration due to gravity. Force applied on the sphere is less, same displacement, less force. Therefore, there is less work. How are we doing so far? Okay. So that's how you answer 4A. Next up on to 4B. So a new pendulum is made by hanging the same small sphere from a different string with negligible mass. Okay. But the new string is elastic. This isn't elastic, this is. And the length of the string might increase depending on the tension. On Earth, it's displaced from theta, and it oscillates with period TE, and it's taken to a new planet, Y. So the radius of planet Y is the same as Earth, but the mass of planet Y is larger. And on planet Y, the sphere is again displaced and released from rest, and it oscillates with this period. Now, this is the paragraph response thing. For each AP physics test, there's one paragraph response. So explain how TY could be larger or smaller than TE. Well, let's go on to our equations for the period of a pendulum. It's 2 pi times the square root of L over G. So let's get back over here and just write that quickly. So period of a pendulum is equal to 2 pi. I don't know what that pi is. It's a good pi. Times the length divided by gravity. Did I get that right? I did indeed. So we know it's the length divided by the gravity. So let's explain how Ty could be larger than Te or smaller than Te. I'm going to start with smaller first. So let's go back to our equation for universal gravitation. And let's look at this. M1 just references the object that the force is being applied to. But let's look at M2. We know that the planets have the same radius. So Earth and this planet Y, same radius. However, planet Y has a greater mass. Therefore, its acceleration due to gravity is greater. So let's write that over here. Planet Y, G, has an increased value. And we can assume that length of strings are similar. Since the only thing changing is the value of G, if planet Y has an increased value of G, it's in the denominator, so this as a whole decreases and therefore the period is less. So this is one example of how the period of Y could be less. So example 1, period of Y can be less than period of E because the gravity is greater and therefore this is going to be decreased, this fraction. But how can the period be greater? Well, we know we're not changing gravity, so the length has to change. But remember, we're told that there is going to be an elastic string. So another argument we can make is example 2. Period of Y is greater than period of E. We know the string is elastic, so the greater acceleration due to gravity on planet Y makes it so that there is a greater force of gravity on the sphere. This results in a greater force of tension on the string. So greater force of tension on string equals more length. Yeah, it's a more length of the string, so more length for the string. And we're going to be arguing that Earth has less of a length. So we're arguing that since on this new planet, because we don't know how much greater it is, we just know it's greater. So if on this new planet, the gravity is so much greater that the tension is actually impacted that much, the length of the string is going to increase so much such that this period is going to be greater. So my main argument here is greater force equals greater string length equals greater value of L equals greater value of T. So that's my main argument for here. So here is just that the G is greater. Here is the length of the string is greater because of the increased force of tension. So question 4 is answered, and now our final question. Question number 5. So at time equals 0, block A slides along a horizontal surface towards block B, which is initially at rest as shown in the figure 1, and the masses are 6 and 2 kilograms. And they collide elastically, so no energy lost at time 1 second. And as a result, the magnitude of change of energy of block B is 9 joules. There is no friction. Find the speed of block B immediately after the collision. So change in kinetic energy is equal to final minus initial. So final minus initial. We know that there is no initial because it's saying, where is it? Block B is at rest. So initial is 0. But we know the final is 9. So 9 minus 0 is equal to 0. 9. I don't know why I said 0. 9 joules. So let's go back to our equation for kinetic energy. So 9 joules is equal to 0.5 mv squared. 9 joules is equal to 0.5 times 2, because it's 2 kilograms, times v squared. 0.5 times 2 is 1, so we just get v squared is equal to 9, and we get v is equal to 3 meters per second. That's the speed of block B immediately after the collision. Now remember, you don't have to say direction or anything because it's speed, not velocity. Now, on the graph in figure 2, draw and label 3 lines to represent the positions of A, B, and the center of mass right after the collision. Well, yeah, right after the collision. So let's see what we have here. Well, let's think about what we know about the center of mass. So this is a position versus time graph, and we know the slope of a position versus time graph is velocity. Now, what do we know about the velocity of center of mass in a collision? The velocity of a center of mass is equal to the sum of momentums divided by the sum of mass. And we know in this collision the momentum is conserved. Therefore, the velocity of the center of mass is conserved. Well, it's the same. So this slope should remain the same. So I'm going to draw this line. It's just going to be the exact same thing. It shouldn't be curvy. It should be a straight line. It's just that it's a bit hard to draw. So let's write CM. Next, we have to say block A. So we calculated the slope of block A to be 3 meters per second. No, not block A. This is block B. So 3 meters per second. So if we want to do 2 seconds, we have a slope of 3. So that means we end at 5. I'm just going to draw this. There we go. So this is going to be block B. And we know since it's an elastic collision, and block A lost all of its energy, block A is going to be drawn like that. This is going to be A. Now, consider in the original scenario, instead of colliding elastically, they collided and stuck together. Describe how the line drawn for the center of mass will change, if at all. Justify your response. Well, I said over here, the velocity of the center of mass is equal to the sum of the momentum of the different objects in the system divided by the sum of the mass. In this collision, momentum is conserved because there's no outside force, outside work, anything. Momentum's conserved, so the sum of the momentum stays the same. And I don't think these blocks are losing mass in the collision, so that also stays the same. So since the velocity of the center of mass stays the same, the slope stays the same, and therefore we draw the line the same way. So let's write this out. Momentum is conserved, mass is conserved, velocity of center of mass is the same, slope remains the same, and therefore the line is drawn the same way. Well, and that's the end of the exam. So that's every question for every solution for every question here. If you have any questions or want further clarification on what I explained or said, please let me know in the comment section down below. Otherwise, goodbye and see you guys later.